All right, in this lesson, we are introducing exponential functions. And so as a warm-up, we are writing an equation for the function given in the table below. And so first, I like to see what's happening in this table. My x's are going up by 1 each time. And then my y's, from 6 to 10, that's 4. From 10 to 14, that's 4. And from 14 to 18, that's 4. And so we can tell this is linear. And then I can tell that the slope, which is the change in y over change in x, is 4 over 1, which is 4. And then to figure out the y-intercept, we just need to go backwards to figure out what value appears in the y column when x is 0. And so 2 plus 4 would give me the 6. And so my y-intercept is 2. And so my equation is in mx plus b because it's linear. And we just discovered that m is 4 and b is 2. Okay, so in general, we learned that all linear functions have a constant difference, which in this case we found is 4, where we are either adding or subtracting, which really is just adding a negative number, a constant value to y each time x is increased by 1. The constant difference is called the slope. Okay, all exponential functions, which is our new function that we're looking at today, will have what is called a constant ratio. Okay, where we are multiplying or dividing. A constant value to y each time x is increased by 1. Okay, so there are actually two types of exponential functions. There's exponential growth and there's exponential decay. Okay, exponential growth can either approach positive infinity or negative infinity. It can be going up forever or it can be going all the way down. Okay, exponential decay has to be approaching 0. Think of the word decay like dying, okay? And so we're going to look at some pictures to kind of really solidify this, okay? And so in these examples, growth, you can see as we go to the right, our function is increasing, going to positive infinity. And then down here, it's decreasing, but it's not decay because it's going away from the 0 line. It's only considered decay if you're approaching 0. Think flatlining, think dying. So here we're starting really low, but as we go to the right, it's dying off. It's flatlining. Same with the blue. It starts high and then it's flatlining. It's dying. It's going to 0. Okay, so think of decay not like decreasing. They're not synonyms. Decay means it's dying. It's going to 0. In this case, this orange function, it's increasing, but it's dying off. Okay, and so an invisible line in math, if you have an invisible line that a curve approaches but never touches, it's called an asymptote. Asymptote. Okay? And so, for example, if we had 0.1, then 0.01, then 0.001, 0.0001, we're getting infinitely closer to 0 each time. But if I keep this pattern going, we never actually equal 0. We're just approaching it. I'm always going to have a 1. But I'm just having more zeros in front of it. Okay, so that's called an asymptote. In general, we have an equation. Instead of mx plus b, it's a times b to the x power. You're going to recognize an exponential equation because your exponent is an x. That's where your x is. It's in the exponent. And so this a value in front is going to be your y-intercept this time. And so if we're dealing with a real world problem, this is your starting value. Okay, and the reason why is if we plug in 0 for x, anything to the 0 power is 1. So this whole number is turning into a 1, and it leaves us with a. So that's going to be our y-intercept. The b value that has the exponent, sometimes they put it in parentheses, sometimes they don't. It's the base of your exponent. That is your constant ratio. And you can think of the word ratio as multiplier. That's the number we're multiplying by each time. So if you want to call it a constant multiplier, it wouldn't be wrong. Constant multiplier, what we're multiplying by each time. So as we multiply by a number bigger than 1, it can be 2, it can be 10, it could be 1.1. As long as it's bigger than 1, it's going to be growth. Okay? If we multiply by a number between 0 and 1, so like 1/2, 1/3. So I'm going to put some examples up here. So like here, 1.5, we could have it in fraction form. We could have 2, we could have 3, we could have 10. All of those would grow. Whereas if our value is like 1/2 or 1/3, 1/10, 2/3, 0.7, all of those are smaller than 1. That's going to be decay. Because if you think about multiplying by 1/2 each time, you're cutting that number in half. And so you're getting closer and closer to 0. So anytime you're multiplying by a number smaller than 1, you're actually dividing, which is going to cause you to approach 0 instead of move away from 0. Okay, and so looking at some examples, we're given equations, we're given tables, we're given graphs. We're trying to decide if these represent growth or decay. And so in order to do that, we want to look at the b value. Okay, and so in this case, our b value, our number with the exponent is 4. And so that's going to grow. Okay, looking at this next number, or next example, 3/2 to the x power, that's also going to grow. It's bigger than 1. It's a fraction, but it's bigger than 1. Your numerator is bigger than your denominator. Here, our b value is 2/3. And so that's going to decay. In this next example, b is 0.2. And so that's also going to decay. Anything smaller than 1 decays, and you're never going to have a negative value. I didn't mention that. If b has to be positive, we don't multiply by negatives constantly for exponential functions. In that case, it would be like oscillating from positive to negative, positive to negative. So b will always be positive for these examples. Okay, this next one, we have a picture of the graph. It starts high, but it's going to 0 as we go to the right. And so that is decay. This next example, it starts at 0, but it's moving away from the 0. It's decreasing. So I'm going to write decreasing on here, but it's still considered growth. So it's actually decreasing growth. It's getting further away from 0. So if you think of it like debt, your debt is growing. You're getting very, very negative. Okay, looking at our table here, I can see I'm going from 0.16 to 0.8 to 0.4, so that is growing. Here, we're going from 200 to 20 to 2 to 0.2 to 0.02, so that would be decay. Okay, so this says identify the y-intercept and determine if it's exponential growth or decay. So we've done the growth or decay. Now we just need to identify the y-intercept. It's always your a value. Okay, when you have a times b to the x, that's your y-intercept. So 0, 3. Here, my y-intercept is 1/2. So 0, 1/2. Here, my y-intercept is 10. In this next example, my y-intercept is 1.5. Okay, looking at the graph, that's even easier. I see my y-intercept is 0, 3. In this next example, I kind of colored over it. My y-intercept is 0, -5. looking at my table, remember we're looking for where x is 0. And so my y-intercept is 0, 4. And then in this last example, I see my y-intercept is 0, 2. All right, so in this next part, we are going to find more attributes beyond just growth and decay in the y-intercept. And we're going to do that from a graph, from an equation, and then just from a table. Okay, and so the first example, we have the graph. And so just by looking at the behavior, it is moving away from the 0 line. And so this would be growth. And then we can see clearly that the y-intercept is 0, 3. And then our common ratio, to find that, sometimes it's obvious, sometimes it's not, but I like to go ahead and make a table of points. And so right now, the only point I've pointed out is 0, 3, the y-intercept. And then if I go over to the 1, I see that the value is 6. So x is 1 when y is 6. And so a lot of people could tell, okay, to get from 3 to 6, we are multiplying by 2. And so my common ratio is 2. The other way, sometimes it's not obvious like a 2. Sometimes it's 0.85 or 1.05. And so what you can do is take your y-intercept, that's your y1, take your second y value and call that y2, and you're going to get your b value, the common ratio, by dividing your second y by your first. So in this case, 6 divided by 3 would give us that 2. Okay, and so we have our common ratio, which is 2. We have our y-intercept. And so now that we have our a and our b, we can write our equation y equals a times b to the x power. Okay, and so don't switch those. Your y-intercept goes first, your common ratio goes second. Okay, this next example is asking us for f of 3. And so remember, when you are given the number inside the parentheses, you're given your x value. And so they're wanting to know what is the value of function at x equals 3. So we can continue our table by following the pattern in order to figure that out. We would go to 2, then 3 in the x column. And so we just continue multiplying by 2. And so that would take us to 12 and then to 24. And so f of 3 is equal to 24. The other way to do that is to take your equation and substitute 3 for the x value. Okay, and so that would give me 3 times 2 to the third power. Okay, and so 3 times 2 to the third power is multiplying by 2 3 times. So that would be 6, that would be 4, and then multiply those and you get 24. So either way. Okay, for domain and range, the domain of all exponential functions, if they're giving you the whole graph, goes all the way to the left, all the way to the right, forever. And so your domain is always all real numbers. So if they're just giving you the equation and asking for the domain, it's all real numbers all the time. And then for the range, you actually need to know where the asymptote is first. And so what I like to do is I go to my graph and I look at where the function is flatlining and I continue that line. Okay, and so this is the y equals 0 line, just like this would be the y equals -5, and then this would be the y equals -10. And so y equals 0. You're always going to have a y equals equation for these horizontal asymptotes because they're horizontal lines. And so once you have the horizontal asymptote, your range will match that, only it'll be an inequality. And so for this example, we are above the asymptote. You're either going to be above the asymptote or below it. In this case, we're above it, so we're going to do greater than 0. If it were below down here, we would say less than 0. Okay, so for this next example, we are given the equation. I can see right off the bat that my y-intercept is 4, and my common ratio is 1/2. Okay, common ratio is 1/2. My initial value is 4. So I'm going to fill that in on the table. And then while we're here, I'm going to go ahead and fill in some other values. If we keep multiplying by that common ratio, we would get 2. Multiply by 1/2 again, we get 1. Multiply by 1/2 again, we get 1/2. So I'm just adding that to the table because they do ask for f of 3. And so now at f of 3, I can see my value is 1/2. Domain we know is all real numbers all the time. And then for the asymptote, we can see that this graph is approaching 0. So it is decay, it is approaching 0, and so that's going to be our horizontal asymptote. And for algebra 1, it typically is always y equals 0, but later in these notes, I'm going to show you examples that don't have y equals 0 as an asymptote. And then you can see all these numbers are positive. If we were to go backwards, we would go to 8 and 16. And so all of these are positive values. So clearly all of our y values are above 0. Some ways they've said it is just all positive real numbers. It says the exact same thing. Y is greater than 0 is the same thing as saying all positive real numbers. All right, and then in this last example, we are just given the table. And so we can see by the y column, this is growth. Our values are growing. Act like this is your bank account. It is growing in value. We can see our y-intercept is 0.7. And then our common ratio. Some people can notice that this is multiplying by 3, but again, call this your y1 and this your y2. You can always find your common ratio by taking y2 divided by y1. In this case, it would be 21 divided by 7, which would give us 3. And so here our common ratio is 3, and so now we can write our equation. We know that A is 7. We know that B is 3. And so we can write our equation 7 times 3 to the x. You don't have to use the parentheses. Sometimes they don't. You can just use a multiplication dot. You just need some way to show that you're multiplying. Okay, and so to figure out f of 3, we can continue our table. We would just need to multiply 63 times 3. And so 63 times 3 would give me 189. And so now we have the f of 3 is equal to 189. Domain is all real numbers all the time. And then our range, once again, all these y values are positive. And so it is all positive numbers or y greater than 0. And then our asymptote, again, is y equals 0. All right, in this last section, we're actually going to create the graphs ourselves. And so given the equation, we need to be able to create the graph. And to do that, it's helpful to identify this information. And so looking at this first example, I just see 2 to the x. Usually we see 2 values, an a and a b. And so notice this 2 has the exponent. That means 2 is our b value. Okay, and you're not seeing an a value, that means it's an invisible 1. And so in this case, our a value is 1, which means our y-intercept is 1. It's a common mistake. Some people say the y-intercept is 2. And so if you don't see 2 numbers, put the number in parentheses that has the exponent and write your invisible 1. So there's my y-intercept at 1. Okay, and then my b value is 2. And so if we wanted to get some more points to create our graph, we start at the y-intercept, and then we are doubling each time. So we just need to keep multiplying by 2 until we have enough points. So at 1, we would be at 2. At 2, we would be at 4. At 3, we would then be at 8, just doubling these y values. So I can also graph 1, 2. I can graph 2, 4. And then I can graph 3, 8. And so you see it's growing as we go to the right. And so as we go backwards, we have our 1/2, we have our 1/4, we have our 1/8, we have our 1/16, 1/32, 1/64, 1/128. So we're getting really, really close to 0, which means our asymptote is y equals 0. Domain, all real numbers all the time. I'm going to start using the symbol just to save some time. And then for the range, we are above the asymptote. So we're going to say y is greater than 0. Okay, for this next example, we do see what our a value is. It's -9. And we see our b value is 1/3. Okay, and so we can go ahead and write in our y-intercept 0, -9. And so going down to -9, there's our y-intercept. And so we know by looking at the b value of 1/3, it's going to be decay. But let's get some more points to graph. Okay, and so we know we're starting at 0, -9. And then each time we increase x by 1, we are multiplying by 1/3. So 1/3 of -9 would give me -3. And then 1/3 of -3 would give me -1. And then 1/3 of -1 would give me -1/3. And so I can also graph the point 1, -3, 2, -1, and then 3, -1/3. And so you can see once again, we are approaching the 0. So it's an increasing graph, but it's still decay because it's approaching 0. It's flatlining. Okay, and so our domain, all real numbers. And then our range, this time we see the asymptote at 0, but we are below it. So we still have the asymptote at 0, but because we are below it, we're going to use a less than sign. So what I like to do is I like to write the word below with a less than sign, because anytime you're below, you want your less than sign. All right, so these next examples are the examples that have an asymptote that is not 0. For Algebra 1, we only look at equations that are a times b to the x. There's no plus number after. Here, you're seeing a +3. In this next example, you're seeing a -8. That actually tells you the asymptote. So instead of y equals 0, this first example, number 3, has an asymptote at y equals 3. And so you can graph an invisible line. Sometimes we use a dotted line to show that it's not actually showing up. It's just an invisible line we approach but never cross. And then in the example for number 4, it's y equals -8. So we can draw an invisible line at y equals -8, and we know that the graph is going to approach it. Okay, next, to find the y-intercept, you're starting with your y-intercept at 4, but you also have to add 3. And so your new y-intercept starts at 4, but +3 would give us 7. And so our y-intercept for number 3 is 7. And so go ahead and graph that. And then for number 4, we can see that the y-intercept is 4 minus 8. 4 minus 8 would give us -4. And so our y-intercept is -4, and we can graph that. Now, looking at our b value is 1/2 here, and so we know it's decay. That is smaller than 1. And so when you're creating your graph, make sure you are approaching the flat line as you go to the right and moving away as you go backwards. Okay, and so our domain, still all real numbers. That's not going to change. Still all real numbers. And we are above the asymptote. So this time the asymptote is 3, and we are above it. Y is greater than 3. Okay, and so your range should always match whatever value the asymptote is for exponential functions. Okay, for this next example, we have our b value is 3. We know that's growth. That's bigger than 1. And so as we go to the right, we're moving away from the asymptote. And as we go backwards, we would be approaching it. Okay, and so we are still above the asymptote. And so that is greater than the asymptote at -8.